Good morning, majors. Today we're going to go over our day 2 notes, and this should be the end of your notes for the year. This is it. So I want you to read these. We are going over rotation today and symmetry. So this is a rotation. Usually we rotate it about the center of the coordinate plane, which is the origin. It says a rotation is an isometry. If you remember from day 1, an isometry means that the figures are going to be congruent. So they're going to look exactly the same. So say we have something right here, this point, and maybe it is at 1, 2, 3, 4, 5, 3, 5, 3. We have to remember to put parentheses around our numbers to make it an ordered pair. So this is 0 right here. And if I rotate it to right here, it's going to be at negative 3, 5. So there's a formula that we're going to see, or a pattern. So I'm going to go negative 3, 5. This is going to be our rotating it 90 degrees. And this would be 90 degrees counterclockwise. So when we go to the left, this is called counterclockwise. When we go to the right, this is clockwise. So this right here is 0 degrees. This one is 90. This is 180. This is 270. And then if we go back one more, 90 is 360. All right. So if we rotate it another 90 degrees, then we will be at negative 5, 3. Negative 3. So we'll be right here. And if we rotate it another 90 degrees, then we will be at 3, negative 5. And you can kind of see that it makes a circle. We're following a circle. So when rotating about the origin, the 0.53 goes to, and they'll ask you something like this on the SOL. It depends on how far and which way we rotate it. If we rotate it 90 degrees counterclockwise, remember that is to the left, then it's going to go to negative 3, 5. 270 degrees counterclockwise is right here, and this is 3, negative 5. 360 degrees just means it's going to go around the circle one whole time, and then it's going to end where it began, which is at 5, 3. And then 180 degrees means we're going to rotate it twice, and this is at negative 5, negative 3. All right, so let's do an example. It says, name the coordinates of the vertices of the image after the given rotation about the origin. So we're going to use the center, the origin right here. So 90 degrees clockwise. Let's find each one first. A is at 2, 0. And when we rotate it 90 degrees clockwise, now we're going to be at 0, negative 2. So we're going to be right here. When we rotate B 90 degrees clockwise, we are at 2, 5. 2, 5. And when we rotate it, that is going to be 5, negative 2. And then C, I'll try to see over here, is at 6, 5. C will be at 5, negative 6. If you connect these dots, they will be the same figure rotated 90 degrees clockwise. 5, -2. So just connect these. They're going to be the same thing. Use a ruler, guys. This will help if you use a ruler. It's the same figure. You guys can try this one. Okay, a rotational symmetry means this triangle, how many times or what is the smallest degree that I can rotate it so it'll land exactly onto itself again. So we're going to say a figure has rotational symmetry if a turn about the center point of 180 degrees. It has to be less than 180 degrees. 180 degrees or less maps onto itself, so it's going to look like itself again. All regular polygons, regular means that the polygons have equal sides and equal angles and parallelograms. Does the figure have rotational symmetry? So if we rotate an isosceles triangle, if we rotate it upside down 180 degrees, it'll look like this, right? So it doesn't really look like itself. If it was a equilateral triangle, it does have rotational symmetry, right? These do have rotational symmetry, but this one does not. A rhombus does. If you rotate it 180 degrees, it's going to look like itself. A regular hexagon does. Yes. And if you rotate it 60 degrees, it'll look like itself. It'll move it from this point to this point. So every factor or multiple of 60 will work also. If you rotate it 120 degrees, it'll make it go to this spot right here, this one to this spot. So 60, 120, 180, and so on until you get to 360. A star, this star does. And what we're going to do, how many times can I rotate it within the 360? What I'm going to do is say, well, 360, the star is even, and we have 5 vertices, so 360 divided by 5 equals 72 degrees. So every 72 degrees, the star, when we rotate it, will look exactly like itself. I want you guys to try the rest. All right, and we'll try maybe one of these. This is going to be classwork. We're pretty much done. So I'm going to try a couple out and see how it goes. So this one, it says, name the image under the rotation described below. So let's try 4. AB, what does AB go to when you rotate it 120 degrees clockwise? So clockwise means we're going to the right? And 120 means we're going to move it. Each one is 60. Let me just show you this. Each one is 60. So 120 degrees is going to move AB to CD. So this is 2 rotations. So this is going to be now CD. FE, 60 degrees counterclockwise. So counterclockwise means we're going to go the opposite way. We're going to start at FE and we're going to go this way 1 time. 60 degrees is just 1 time. And so this is going to be AF. Okay? And I want you guys to try C. What happens when we work with C? All right, guys, this is about it. I hope you guys have a great night and you study for your SOL.